So first things first, I am going to have like a bunch of code on slides, which can get hard to read. If you're having trouble seeing the presentation, you may want to like grab one of the chairs and drag it up here so you can get a closer view. Just fair warning, there's a bunch of code here. The other thing I want to say is, just as way of introduction, I don't know if anyone here knows who I am, but I work on C++, but I also work on LLVM. And this presentation is actually very near and dear to my heart. I work on the LLVM optimizer, and so this is my chance to kind of explain to people how it works. So how many folks here took a compiler's course at some point in their lives? Yeah, everybody. Well, almost everybody. How many folks here didn't take a compiler course? Smart people, okay. So this was my textbook, okay. I don't know, how many folks here had this textbook in their compiler's course? Yeah. So say what? Read it anyways. It's a good textbook, but it's kind of a little misleading from how I view compilers. Because in this one, right, we have this dragon here that's supposed to represent kind of how hard it is to build a compiler. And we've got a bunch of techniques for dealing with that. There's like armor and a sword that this knight's going to use to figure out how to build a compiler. But if you actually look at this is all about the complexity of building a parser. Not really the complexity of like generating good code. And it turns out that I'm not that interested in parsing. I mean, it's interesting kind of academically, but that's not where my heart is. And so this wasn't really that good for me. I was more interested in how you optimize code. The other problem is that this dragon seems really friendly. Like, he's kind of grinning, a little toothy, like, I don't know. But like, I kind of imagine the complexity of compilers more like this, right? Like you're getting torched, right? Getting kind of cooked, I don't know. So what I want to talk about is what I find to be one of the most complex parts of the compiler, which is how the compiler optimizes your code. And it's kind of important to understand that in order to understand the performance of your code. How many folks here don't care at all about the performance of their C++ code? It's okay, you don't have to be shy. Anyone? Good, that means you're not using a completely terrible language for what you're trying to do. But if you care about the performance of your code, right, you actually need to understand how the compiler works. Otherwise, you're just not going to understand the performance of your code. And so this talk tries to help teach you a little bit about that. But I do have some caveats. It's going to teach you a little bit about that from kind of my perspective on code, on compilers, which involves teaching about LLVM, not about GCC, not about other compilers. I'm going to try and give you a little bit of background when something is general to all the compilers I'm aware of versus very particular to LLVM. But I do have some bias here. Like I don't work on GCC. I'm not an expert on it. The other thing I do want to kind of clarify is that like there are a lot of parts of the compiler. And we're not going to be able to talk about all of them tonight. And in fact, I don't know how much we're going to get to go through just of this stuff, but we're going to try and focus on a very particular part. So if you took a compiler's course, they often will break down a compiler into several pieces. The front end, right, responsible for parsing, for all the semantic analysis, all the stuff that the Dragon book really focuses on in terms of compiler complexity. And there's also a code generator that has to deal with like register allocation and other kind of tricky problems, very traditional problems. The Dragon book also touches on this, right? And we're not going to talk about either of those. Okay, we're going to talk about this weird middle piece that's the optimizer that sits between the front end and actually generating code. So it works in a fairly abstract space, and it's kind of the lesser known component to compilers. So that's why I want to focus on this. I think of this as essentially optimization 101. Okay. Oh, so the other thing I should clarify, like I want you to ask questions, right? Like if something doesn't make sense, please stop me and ask questions, and I'll try and dig into it and explain it. This talk doesn't make a whole, like isn't really useful without that. All right, so here's my example. Now it's kind of sad, I give this talk at a C++ user group. I have an example here that doesn't use any C++ code at all. But it's still useful, right? Like the C code is also C++ code. This is a pretty simple, everybody understand what this code does, right? This is trivial, right? So if you compile this code with Clang, you can actually get it to dump out kind of its front end state. And it looks something like this, but for like 8 more pages. Because the front end really is complex, right? The Dragon book wasn't making everything up. Like parsing is actually hard, C++ parsing is even harder, but there are some things in here we can kind of see that make some sense, right? We see stuff like we have this not equal to, right, argc, and the value 3, like you can kind of piece together where some of the code went into this. But the optimizer can't look at this. There's way too much data here, and most of this doesn't even matter, right? Most of this is about like file lines and columns. This isn't really relevant to optimizing your code. So we take all of this down and we reduce it to kind of an intermediate form for LLVM. This is called LLVM's IR. And this is the actual IR for the program you looked at. But none of this makes any sense, right? Like I've got a bunch of words here in a vaguely programming language looking thing. So before we can even have kind of a conversation about how the optimizer works, we actually have to have a conversation about how LLVM even models your program. How many folks here know anything about LLVM's internals? I'm expecting like a few hands, right? So for the rest of you folks, this is going to be really cool, because at the end of this talk, you're going to know a lot about LLVM's internals, okay? That's actually step one. For the folks who do already know, you can heckle me, that's fine. Okay, so let's describe LLVM's intermediate representation, right? This is kind of how it represents your program inside the optimizer. You'll see this called IR all over the place. Okay, so we start off very simple. Anyone who knows programming languages is going to look at this, they're going to understand what's going on here. We've declared a function, it's got some goofy syntax. I'm not going to try and teach you how to parse LLVM IR, right? But you can see what happens here. We've got a function that we declare. We define another function f. It takes parameters. We have types, kind of looking like a C type. It's a little bit more explicit. This is a 32-bit integer type, right? You've got a basic block here, and we'll talk more about what that means, but you've got, addition, so we're adding two things. We're calling a function here. We're getting the result of that, right? We're adding more things, and we're returning something. It's pretty straightforward, right? Nothing kind of crazy going on. Yeah?
Why was the basic decision made to convert it into a register function or operator type of language versus the stack-oriented language?
Oh my goodness, that's a long question. Can you write that down and ask that again at kind of the end of the talk? Because I don't even know where we'll start with that. I want to answer it if I can though. It's not going to impact the actual talk. It's just good background. Okay, so let's keep going a little bit here. Let's look into more of the IR. So you've got basic blocks, right? And anyone here not know what I mean by a basic block? Cool. Then I won't try to explain. So we've got basic blocks. Right? We've got three basic blocks here. We always give them names, right? You have entry and then and else, right? And each basic block in LLVM takes a very rigid structure. You start with a sequence of instructions and you end with a special instruction that transfers control flow somewhere else. All right? And that's how you can stitch together these basic blocks to understand the control flow of a function. So here we come into the entry, we branch on a conditional flag, right? So this is a conditional, like an if. And on one hand, we go to the then block. On the other one, we go to the else. Pretty straightforward, right? I1 is just 1 bit, right? So on the then block, we come down here. We have a call. We return. Return transfers control flow to the caller, right? Else, we have another return. Make some sense? It's a pretty straightforward control flow graph. Nothing too fancy. All right, so this is all great. There's one more kind of interesting thing that we have to talk about here, though. These labels, this %d thing. It seems like you're just doing assignment, but it's a little bit more important, fundamental to LLVM's IR than just assignment. This is what's called single static assignment or static single assignment form, SSA form. And that means that these aren't assignments, these are labels, okay? You can't change the meaning of a particular name. So this %c here is the name for this instruction. You can't ever reuse it. You can't have some other instruction down here that is also called %c. So it's not assignment, it's actually much more like labeling or binding a name. And this is really fundamental to the IR. Every name is just a name of something that produced that value. So when we talk about this add instruction, we actually just talk about %c. That's the name of the add instruction. Right? You can always refer to it from anywhere, right? When you say %c here, we know that this is passing the result of the add because you have that name. Make some sense? Everybody happy with this? Yes? It is passing the result of that specific add. I mean, clearly, right, this function can be executed with different arguments. That result could have different values each time. But when you execute the function, that add gets a name, and we pass the result in here, right? No matter how many times we use it, like we pass the result in here, we return the result here, this is referring to the same operation, right? So it is still very symbolic, right? Now the tricky part is if you can't assign anything, right? If you have this like fixed labeling, how do you handle merges in the control flow graph? Right? And that was kind of the invention that made SSA interesting. And it involves this weird operation called a phi node. Okay? And what a phi does is it actually looks at where control flow comes from to select a value. So here we have same function as before. We have this entry block and a condition. We go to then or end. Okay? But at the then block, we actually merge control flow back into end. Okay? So this end basic block has two predecessors in the control flow graph. It can either come from entry or from then. Well, the phi node actually models this. It says if control flow comes from the entry block, I take on whatever the value of %c was. Okay? If control flow comes from the %then block, take on the value of %d. And this kind of capturing of this value takes place on the control flow edge. Okay, it's a completely notional operation. As you flow into this block, the edge you flow on will determine the result of this entire instruction. Make some sense? And now we have single static assignment form, where we always have one name for every value in the function, right? We never have two names for a single value, and we never reuse a name. And so we can use this to do very interesting data flow analyses. Yes? So the question is, must the phi node come first? Yes, the phi nodes have to come first. Now, you can have a bunch of them, but they have to come first. And the reason they come first is that phi nodes really are kind of notional instructions. They don't execute in any real sense, or if they do execute, they don't execute within this basic block at all. They actually execute on the control flow edge entering it. We can get into complex examples that show why that matters, but yeah, you can just think of them as coming at the top. Everybody happy with this idea? Vaguely? Okay. So, here's the cool part. We're done. That's all of LLVM's IR. Like really, that's it. There are no other important concepts in LLVM's IR. They're like different operations, right? We have add here. There are a bunch of other things you can do. They don't matter. You don't need to understand all of the operations to understand the semantics of the IR, right? There are other things besides a conditional branch, but none of them are meaningfully different. Right? They all work the same fundamental way. Phi nodes all work the same fundamental way. So this really is all of the important concepts of LLVM's IR. Yes?
How about loops?
Even including loops. And we'll even talk a lot about loops. Don't worry. But yes, this includes looping, which is really wild. It's a very reductive representation. And that's useful because it simplifies building an optimizer. The optimizer has to reason about very few concepts when actually understanding your program. Okay, so where were we? You guys are now LLVM IR experts. You're all awesome at it. All right? Hopefully this has already been productive for your evening. All right, here we go. So this is the IR for Hello World that we were looking at. Unfortunately, this IR looks absolutely nothing like anything I showed you. And that actually leads us to the first interesting aspect of the optimizer. See, the optimizer doesn't just make your code fast. That's actually only one of several different jobs the optimizer has. Okay, it actually has an initial step, which is cleanup. So front ends are already really complex, right? That front end layer is already really complex. Clang has a lot of complexity in it. We try to sink as much complexity out of Clang as we can. And one way we do that is by letting Clang emit really dumb IR. Like just preposterous IR. Because we trust that LLVM will go through and clean it up. So Clang doesn't actually do the whole SSA for it. It literally can't generate SSA for it. Instead, it just writes everything to memory somewhere, and it lets the rest of LLVM clean up after its mess. So the first step of this is cleanup. So if we take this C program or C++ program and we compile it, we get this kind of pile of goo where it's actually allocating memory for every single value in the entire program, storing like trivial constants to them just to load them back out of the memory, right? There's no reason to do this except that it makes the front end simpler, okay? And LLVM's really good at this part of its job. So when we do the cleanup, it turns into this, okay? There are a bunch of things that happen here, but mostly what we did was we took away memory allocations and we replaced them with SSA values, these labeled values. And that removes a bunch of the complexity from the code. So now this is actually probably starting to look like the IR we talked about, and we can even see where we get the code from. So we start off with a comparison for an integer not equal to 3. Well, here we have a comparison that an integer is not equal to 3. That kind of makes sense. Based on the result, right, we do a branch. That also lines up. We have this if here that controls two different results. We have this if-then, right, which is the, if it is not equal to. We go to return, and we have and if we look at return, we have a fee, so we're picking up the data from where we came from. We get -1 if we came from if-then. Cool, we're supposed to return -1, right? This actually makes sense. And on the other side, we have to do a bunch of work to call these two functions and to add their results, right? And we have to do some loads here in order to index an array, right? This get element pointer is probably the most horrific instruction you will see up here today. This is a crazy built-in operation LLVM has to do array indexing. That's all it does. It takes a pointer and it does crazy amounts of array and struct indexing and gives you a new pointer back. And once you do that, you can load through it. And so you'll see this as basically a fancy way of doing pointer arithmetic before a load. Make some sense? Everybody vaguely happy with how this works? Yeah?
Can you back up to where the first thing
Feet node.
Yeah, the parameters are in a different order.
Parameters are in different order. You're right, the parameters are in a different order. But here's the crazy thing. Why does it matter? This is a notional thing that is evaluated on the control flow edge. So we don't actually evaluate like all of these parameters. We're just assigning this, we're just building an association between edges into this and values that come along those edges.
You don't care.
Oh, I got the orders that way. Yes, sorry. I just typed my code wrong. Sorry. Sorry. That one's correct, because that one came out of LLVM. I didn't type this. I typed the other one. I'm sorry. One of these is a label of a basic block, though. The other one is not. So it still is just an association. It doesn't really matter what the order is. Anyways, everybody happy? And well done, you did in fact troll me. I appreciate it. Found the bug in my slide. Okay. So once we've done our cleanup, we have to do the next thing, and this is called canonicalization. This is a really interesting part of the compiler. I'm not going to spend a ton of time on it because it's a little bit boring, but it is more important than a lot of people realize. This is probably the most one of the easiest things to get wrong in a compiler, and this is also a place where LLVM kind of is unusually good as compilers go. It does a little bit more canonicalization than a lot of other compilers, and that stems from it having a very minimalist IR. The two things go hand in hand. The more minimal your IR, the more you have to do this, and we'll kind of see where that comes from. So what do we mean by canonicalization? There are a million different ways you can write the same fundamental operation. So here we have a bunch of code that all implements the same operation. I mean, questionable coding styles aside, these are all equivalent, right? These aren't different operations. And we don't want to have to teach the compiler or the optimizer how to recognize all of these different operations and turn them into whichever one is most efficient, right? We want it to be able to see a single pattern for all of the things that are equivalent. Otherwise, we have this enormous explosion in the state space that the optimizer has to recognize, right? And so canonicalization is very simply the process of trying to recognize different patterns that mean the same thing and replace them with a canonical pattern that is expected to mean that thing in the rest of the optimizer. Okay? And we do this very, very heavily in LLVM's IR. With a more minimal intermediate representation, you have more possible ways to say the same thing. You have larger patterns that you're using to represent more complex things, right? And each piece of the pattern introduces some variability, right? And since it's, combinatorial, you get a really large explosion for a really minimal IR. And so LLVM has to work very hard to actually canonicalize effectively to kind of keep its optimization complexity in check. And it seems to do so empirically. All right, so let's look at how this works in a real, yes?
Previous slide, on the left bottom, did you mean inside of if x assumes the value of y? X instead of z?
No.
No.
No. That one was the hardest one for me to read through too, but I'm pretty sure it's correct.
No, these are actually all the same. I mean, sure, this will update z.
It has a side effect.
But we can assume that nothing's reading that if that was correct.
So what's on the left is equivalent to what's on the right.
Yeah. You can assume that all of these things are totally equivalent to this, including all the side effects they have.
On the right, we assume put I the value to x. On the left, we assume z to x, but y to not to x, but to z.
That's the only one that alters the.
This alters z, but it still puts x into the same state. Yes.
But it's not equivalent to what's on the right, because on the left, z is not updated.
Sure. This is part of the problem, right? If I could see the rest of the code, maybe I can prove that z is not updated and all these things are the same. But I don't want to think about that. I want them all to look the same. If if this update to z is not important, right? I don't want to have to reason about it here. I want to look at this, right? That's the idea. It's these complexities that we're trying to get rid of by canonicalizing, so that it's much easier to look at the code and assume what it does. Also, this is just an example. Don't get buried here, okay? I didn't even give z a type, or y a type, or flag a type. So technically speaking, all of these are radically different, but that's fine, okay? That's totally fine here. Yes?
I'm curious, how do you represent thrown exceptions and things like that?
Oh my goodness, I am not even touching on exception handling. The amount of complexity that brings into the compiler is massive. Some other time. I literally don't even have a single exception handling slide up here because it's just too complex to explain. And it's also too complex to optimize, right? If you care about your code, the first thing I tell anyone to do is turn off exception handling. Just don't do it. I know it's painful, but I don't know of a single compiler that is truly effective in the face of exception handling. Exception handling makes all of your control flow graphs explode with complexity, and it makes optimizing them much, much harder. Anyways, that's a long tangent. There's a lot of discussion to be had there, but I'm not showing exception handling. You can take any exception handling that LLVM models, though, and you can rewrite it to use this basic IR if you wanted to.
But does it do that?
No, we don't.
So the exceptions I'm not asking you to explain the exception.
Sure.
But is it handled by the IR or by some other mechanism?
We explicitly model exceptions in the IR, and the number one reason why we do is so that we don't have to generate a bunch of canonical patterns for them, because our goal is actually to not optimize exception handling code, because we assume it's exceptional, right? So we want to keep it out of the IR to the extent possible, and so we have essentially a minimal representation in the IR to kind of structurally reflect that priority. And so that's the other reason why I don't show it, because it's not actually relevant to how well your code optimizes, because it works very hard to move all of the exceptional edges out of the IR and leave the remainder. We can debate whether it does enough of that. Anyways. Okay, we're gonna keep going. So let's see how this canonicalization stuff actually plays out in practice. So we have our original thing, so we've cleaned it up. So we have the form that makes sense from our kind of explanation, right? But we need to canonicalize this. And there are a few things that can be kind of just made much more canonical in this IR. The first one is up at the very top, this not equal to. So not equal to and equal to are kind of the same thing for integers, right? There's not really an interesting distinction for integers. We'd like to not have to add 2 versions of every single thing that cares about equality tests in the entire optimizer. And so we don't do that. We just switch everything that is not equal to be equal to. So we take this not equal to comparison and we turn it to equal to. Now how do we do that? So when it's not equal to, we have then on the left-hand side of this conditional branch, we have end on the right-hand side of this conditional branch. Well, if we invert the comparison to be equality, we have to invert the destinations of the branch. And so now end is on the left-hand side and then is on the right-hand side. Very simple. Now this pattern is canonical, right? So we always look for equality tests, not for non-equality. The next thing is kind of the control, and there are a million different canonicalizations for different kinds of expressions, but they all look essentially like this, right? They all take one expression and replace it with another expression that's somehow more canonical, right? The second kind of canonicalization we do is with the control flow graph itself. So like here we have this empty, useless basic block. It's just cluttering up everything, right? We want to assume that those don't exist, so we don't have to keep scanning across empty basic blocks to find some instruction that actually does something. And so we also kind of canonicalize the control flow graph. So we take out that block, we thread it directly into this phi node, so that now this comes from entry instead of that separate block. Yes? I'm sorry? Well, no, because we removed one predecessor, right? So we had a then, if then as a predecessor, right? And it was in the phi node. And we removed that, and now entry is the predecessor. And so we just have entry in the phi node.
Often people write code so they have the early exit, like if something returns a function, that's
Yep.
a hot path.
Yep.
But if you rotate it so the return is down to the end, the optimizer knows what's the hot path.
We rely on more semantic things than just the structural stuff that comes out of the front end. There's a long discussion about how those semantic things work, but we rely on semantic hints. Yeah. So we do lose some source structure here, right? But it's intentional. That's the whole point of canonicalizing. Canonicalizing is in the business of removing the way the programmer wrote it and replacing it with a canonical pattern the optimizer has been taught to recognize. Yes? So yeah, you have to find some other semantic way of conveying that information if you want to convey it. And there are various ways of conveying that kind of information through the IR, the whole pile of them. And because those are semantic, when we do this, we have to update that information to remain accurate, and we do. Okay, everybody happy with this? A bunch of LLVM hackers in the back of the room slowing us down. Okay, so it's fine. I'm just teasing back. So we've gone through cleanup and canonicalization. But those aren't really why I want to talk to you guys. It's not that interesting. Like there are more interesting parts of the optimizer. The third big job of the optimizer is collapsing abstractions, things that programmers wrote that don't really matter and get in the way of actually producing fast, efficient code. And this is also particularly important for C++, because C++ has this often quoted promise of zero-cost abstractions. And that's a total lie. Right, you all realize this is a total lie, right? And the way that we kind of sort of, pretend that it's not a complete and total lie is by leaning on a compiler to collapse those abstractions back to zero cost when it can do so, right? That's how this actually works in practice most of the time. And so this is a very, very important part of the optimizer. C++'s performance relies incredibly heavily on this actually taking place. Make sense? Okay, so we're going to focus on this for a little bit. In order to do this, we need to actually know what abstractions we care about. I'm going to claim, this is a somewhat bold claim, so you may not agree with me, but I claim there are essentially 3 key abstractions in any piece of software. Okay? So 3 key abstractions are function calls, right? This idea of having a call graph, memory, loads and stores, and loops. Okay? And there's a reason why I think these are the 3 key abstractions in the program. Okay? Let's think about how computers compute. Let's go to first principles. How does a Turing machine work? Well, you need a tape. Usually we represent tape as memory with loads and stores, right? You need branches and iteration, right? And those tend to look like loops, okay? And the interesting thing is you don't need functions or function calls. This is not necessary to build any actual computational program, which is interesting because that means this is completely artificial. This is an abstraction introduced purely for programmer benefit. It's not part of the computational machine, right? That means of all of the things we have to actually optimize, function calls are easily the most important thing to optimize that the programmer puts into the code because they are not part of the computational machinery of the processor, right? At the lowest level. Make sense? So we're going to start there. Let's start with the most important stuff. Oh, and I should mention there are a lot of other techniques in optimization. There's a lot of interesting stuff in optimization. I'm not talking about it. Sorry, I have to pick and choose. I'm going to choose to talk about collapsing abstractions. All right, let's look at function calls and how we collapse them. So the optimization to collapse function calls and the abstraction they form is called inlining. It's really straightforward. You take function call some other function, you take the body of that function, and you just splat it into the function that called it. Just take that call instruction, rewrite it with the body of the function it was calling. It's really straightforward. It's great. All right. It should be like the simplest thing in the world, which is good because it's literally the most important optimization in any compiler in the world. And I will very firmly state this is the most important optimization in any compiler in the world. This is where all of your big bang optimization wins come from. Just all of them. It's amazing to me. And unfortunately, it's not that easy because there isn't some right way to do this. All right, inlining suffers from the Goldilocks problem. Okay, you don't want to inline too little because then you still have all of these abstractions kicking around in your code. You haven't done anything. You haven't actually gotten rid of the thing you wanted to get rid of, right? So you have to inline some, but how much do you inline? So if you inline too much, you end up making your code look like this, and it's really, really slow for a bunch of other reasons. Unfortunately, computers are really bad at executing, infinitely large programs. And so if you just inline all of the function calls in the program, you end up with something that's useless in practice, even though it's very theoretically minimized and it has no unnecessary abstractions in it. It's not really all that useful, right? It's not good. But this means there isn't this like perfect answer of like, aha, I have inlined enough, right? At no point do we say like, yes, I'm done inlining now. It's a miserable, miserable problem. And I'll note that in Goldilocks, she gets eaten by the bear at the end of it every time, right? And that's how you feel like working on the inliner. So let's talk about how LLVM's inliner works. So the first thing we need to do if we're going to build an inliner is we need to figure out how to optimize a call graph. How do we even reason about a call graph? We're not going to use these instructions, right? Because we have to operate at some much higher level of abstraction from your program. These instructions are way too fine-grained. And the way we do that is we actually use graph theory. So we actually build a literal call graph. And it looks something like this, right? A calls B, B calls C, C calls A, right? And you can see that there are cycles, right? So it's a directed graph, but it's not acyclic, right? So we've got these cycles, and you have this call graph. This is how we begin breaking down the problem of inlining. So once we have this call graph, because there are cycles, we have to apply graph theory to understand how to really manipulate and analyze it. And yes?
Does this graph reflect the transfer of the control from address to address or call between the functions?
Just a call, I mean.
So function B calls C, function C calls A.
Yes. Yes. Yeah, just these edges are call edges. There's of course a bidirectional thing because they call and then return. Yes?
Is this a brand new call graph based on the IR, or is this the original front-end call graph?
Good question. So where did this come from, right? And this is built from the IR. And so we actually clean up all of the IR first, and then we look at the IR to build this call graph based on the call instructions we find in the IR. All right, so the primary graph theory thing we use here is that we would like to process this in a way that gives us as much information about each step as possible. Okay, so before we try and understand how to optimize, like let's say E here, right, and the call edges departing E, so E to G or E to F, we would like for G, for example, to have been fully optimized. Because like if G has a bunch of abstractions that when you delete all of them actually do nothing, that's going to be really different from if G is actually a massive pile of complex code. So we want to try and have this priority system for reasoning about different functions in the call graph. And we do that by essentially building strongly connected components of the call graph. And a strongly connected component are all of the nodes that participate in a cycle, okay, within the directed graph. And then we can build a directed acyclic graph out of these strongly connected components. So for example, here we have 3 strongly connected components, right? The blue component and the red component, or the yellow component, or the left, the middle, and the right component, right? And those are the strongly connected components, and we now have a DAG between these components. With a DAG, we can do things like do topological traversals of it. And so we can actually say, like, we're going to go in topological order from the leaves towards the roots, so that we actually process things in an order that gives us more information when we're actually making decisions. And so this is what we call in LLVM a bottom-up SEC-based call graph walk, which is kind of a mouthful. Yes? These are functions. Yeah, these are functions.
So they're
Yeah, the at symbols. Yeah. But if there is no DAG,
For example, if A equals B.
which calls A, then there is a DAG. It consists of a single strongly connected component. There's always a DAG. May not be a very helpful one. Fortunately, that doesn't happen a lot in real code. So recursive calls are actually fairly isolated in practice. And so this process tends to very quickly form actually a tree-like structure out of the DAG. And as it happens, it forms a very broad and shallow tree-like structure for most programs, right? There are merge points in there, but they don't tend to be very interesting. And the way you process DAGs usually is that you kind of view it like a tree, right? The DAG component is deduplication. Yes?
Is that a consequence that just naturally happens, or is that something that the first 2 optimization steps try and do?
So great question. Is this structural is the structure something that we create or something that already exists? All of my evidence is that this already exists. And the reason I think that this already exists is because, again, functions are a completely artificial construct. Programmers put them in. Programmers tend to arrange functions in a fairly predictable way. That said, you'll see that the call graph would be much different before inlining happens. So we're going to talk a little bit about that. That's probably the biggest thing that actually changes the shape of the graph. All right. Let's go through this a little bit so we can understand the precise nature of how LLVM's inliner works. So we're going to start with an SEC. You start at the bottom or top. It depends on which direction your graphs like to grow. But you start over here with an SEC. And within an SEC, you have a cycle. And so there's no right or wrong order. We just loop over the SEC to try and make the best guess we have, okay? But we try and optimize these functions first, okay? Right? Maybe we do some inlining here, but let's pretend we don't, right? We optimize these functions first. Once we've optimized these functions, once we've canonicalized them fully, once we've deleted all of the dead code, we've got them down to be very minimal, very kind of precise descriptions of what they do, right? We can shift bottom up the call graph to look at the next layer. And so now when we consider this call edge between E and G, we have a lot more information because we believe that G is in good shape right now. Like it's really nicely optimized, right? And so when we're doing this analysis, we can make fairly reasonable decisions, okay? Now the next kind of question here is, what kind of analysis are we actually doing? Well, we're essentially trying to determine the complexity of the code we're about to inline. Because we have to make a trade-off. We have to make that Goldilocks judgment. We have to say, like, so we're going to inline this function. Is it big? Is it like complex? Will it actually benefit us to inline it or not? And this is a guess. We don't know, but we try and make the best guess we can based on all the information available. How complex is this code? Does it make sense to incorporate it directly into the caller, or will that just make everything large with no real benefit? Okay, that's the kind of existential question the inliner has on each of these edges. But that question, like it seems like that question would be where we spend all of our time, but a lot of this time is actually spent moving through the call graph, because these are often artificial. So it might be that G has a little bit of complexity, but like E and D actually look really complicated, right? Until the inliner inlines G into E, until it collapses a layer of abstractions, and then everything disappears, right? Maybe all of this code is dead code, right? And so if we don't move from G, then up to this next layer first, right? Then by the time we get to A and B, right, we won't have effectively optimized this middle layer. And this middle layer tends to be the really tricky one. The abstractions in it from function calls prevent the rest of the optimizer from simplifying it. Without simplifying it, we don't know how complex it really is, so we can't make any further up the graph decisions. So we have to simplify and then inline, and then simplify and then inline in a very careful order in order for these things to kind of interact cleanly. So making some sense?
The decision I would make is instruction set considered at this point, or is that somewhat irrelevant?
There's a bunch of things considered. Not enough, too many. Everything from instruction set to like crazy other things, but.
Well, it can't be reverted. I may determine inline and then information further on says, no.
That's a good question. That's a better question. So can we reverse our decisions? Can we make bad decisions, see how they play out, and then undo them later? And the answer is essentially no. No one's ever figured out a way to do this. If you figure out a way to do it, like call me up, let me know. I would love to talk to you. Everyone who's come up with a way to do this, the outlining doesn't have the same effect as inlining did. They aren't actual reversals. Because the key thing about this inline step is that it doesn't delete G. Like, it doesn't remove a function. It just removes an edge. And so there's still another function out there, right? And then there's a copy of that code in some other context. And like to undo the inlining, you would have to be able to look in the middle of a function and say, like, I see something that looks similar to what G looked like before it was inlined into E. I think I can replace that code in the middle of E with a call to G if I just fix up these arguments and I apply a couple of transformations to the return. That's a really hard problem. It's essentially similarity. And worse, it's similarity of code. And code is Turing complete, and so analyzing what it behaves as is hard, right? So like you hit a lot of really hard problems really quickly trying to build a reversal of the inlining decision. And so part of why we need to have this very convoluted system is because we assume we can't reverse an inlining decision, and we try and get as much information ahead of time as we can.
If, for example, G was also E, you might inline it in one case and not inline it in another.
Absolutely. And you don't want to now just extract that region of code and have duplicated code. That might not be any better, right? If you wanted to really reverse it, you have to like reattach an edge to some existing function, which is really scary hard. Or worse, you've inlined all of the copies, right? Like 10 different copies into 10 different contexts. So you have to actually look across all the different functions and figure out, all these functions actually have a very similar region of code. Maybe we can comment them out, and this is code commenting. And there are whole PhD theses about how to do this, and there are a bunch of cases where you can do it, and none of them cover all of them. And so we assume that the inlining can't be, in general, reversed. All right, everybody happy with this so far? So I want to look a little bit more about how we evaluate complexity. I've said that like complex code, we don't want to inline. Simple code, we do want to inline, but that's a bit too hand-wavy. We need to talk about what complexity we're actually going to be looking for here. So there's some cases which are just trivial, right? Like if I've got a function like f, right, where all it's doing is just calling another function, but with the arguments swizzled around in some trivial way, this stuff we always want to inline, right? So those are kind of easy cases. This is easy to recognize. It's not too hard. But they're more interesting cases. So let's look at an interesting case. This is my favorite example of what the inliner is trying to do. So here we have a fancy sort. Now this is because I've just decided that my standard library sort implementation is garbage, because I know better. Okay. So as a master optimizer of code, what I'm going to do here is I'm going to check if I have one or fewer elements, and I'm going to declare that it is already sorted. And I'm going to check if I have 2 elements. And if I have 2 elements, I know that I can use a single swap to sort this thing. It's amazing. It's wonderful. It's awesome. This is such a better sort. Don't ever do this, by the way. This is a terrible idea. This is just for illustration, right? So you write this code, right? Now the interesting thing here is that this std sort function call, it actually gets inlined. Like in practice, this is actually going to get inlined. So maybe if I'm writing my own fancy sort, what I actually have down here is like the full complexity of like, you know, Intero sort from GCC standard library, or merge sort, or whatever your favorite sort algorithm is. It's going to be pages and pages of code. I wrote it just like this, all right? Now, the complexity of this function is interesting, because if I call this function with an empty vector, this is a real simple function, right? It just returns. If I call it with a vector of 1 or 2 elements, this is a really simple function. Like, this is a trivial function. I would always want to inline that. But if I call it with some unknown number of elements, right, this is going to be a potentially very complex function, right? And that's the kind of thing we're looking for in the inliner. We pick our threshold for complexity kind of arbitrarily. It's a terrible threshold. It has no meaning at all. What we're actually trying to do is identify things that are really, really simple and distinguish them from things that are really, really complex. And we kind of freely admit that everything in the middle we get wrong half of the time, right? Because the functions, if you look at functions, right, they tend to be fairly bimodal. You tend to have a very large number of trivial functions and a fairly large number of complex functions, right? And so those are the 2 that are the most important to identify. And so what we're actually doing is we're trying to set some threshold like that, and then we try and do an analysis of complexity that is contextual. So that we're actually not looking at whether fancy sort is complex, but whether a call to fancy sort is complex. So that when we see some parameter, like this vector, we see that you just created the vector and that we stored a constant 0 into its size. We know how big this vector is. When we then analyze this body, we can see, this call is trivial. I know that because it falls down this path, right? Doesn't matter what else is in the function. And so our whole goal here is to get context-sensitive call site analysis of the complexity of a function. We freely admit that, like, we get it wrong when it's near the border. The key thing is identifying things that are clearly below the threshold and things that are clearly above the threshold. Make some sense? In case anyone thinks that, like, we're really good at this, we're terrible. Like this remains like the least well-solved problem in optimizers. It's awful. It's absolutely terrible. Okay. So why doesn't this work well? Why are we so bad at this? This is one of my favorite examples of things that C++ do that actively impede the optimizer. So here we have a delightful friend from C++ 11. We have a variadic template, this little fella here. And this is going to do something pretty straightforward for variadic templates. Like if you just sit down and write a variadic template, it looks something like this, right? You've got your pile of arguments. You don't know how many. You peel the first one off each time. You do some work with that first argument, and then you recurse. But this isn't really recursion, right? You're calling a different function each time, so it's not recursion. But it's going to just build this enormous stack of calls to ever simpler hash functions, right? It's like hundreds of calls, right? Now, that's in and of itself kind of fine, but let's think about how the inliner works. Remember, the inliner works bottom up. At least in LLVM, the inliner works bottom up. So we start with this one. Well, I've already got a problem here because I've just there's a bunch of code in this leaf function that actually does the interesting mixing of bits together to hash a value nicely, right? Maybe this is like a SHA-1 implementation, something, right? Lots of code though, hundreds of instructions maybe. So that's complicated. Maybe we get lucky and it's just below that threshold. Remember, we're wrong like half the time, so it's just below that threshold. So we inline the last call to this into the next to last call. But the next to last call, it also had some complex code in it, and now we've got 2 piles of complex code. At some point, we're going to keep accumulating code, and we're going to fall over this threshold. I don't know where it is, it depends. But at some point, you roll over this threshold. Inliner has to give up. Doesn't know what to do anymore. Then you get like maybe a bunch more calls in the call stack. Finally, at the very end, you see the initial call to this variadic function. And what happens in practice is you might have 50 arguments here, might even have as few as 5 arguments here, and they're all constants. Like they might all be zeros, right? Something really trivial, like the 8 characters in a string, right? In a string literal. And the optimizer is like, yeah, I've got this. I have interesting context to make an inlining decision. So it goes and it looks, and it's like, oh yeah, no, it's just great. I've got a bunch of constants. All this complex code folds away. But then I just call some other function, right? And so this makes it incredibly hard for the optimizer, because now it has to connect 2 arbitrarily distant points in the call graph, right? And realize that at the bottom of this thing, it's got constants that will delete all of the math. And at the other end, it has nothing but math, right? It's a perfect inlining candidate. It's an abstraction that a programmer wrote because they didn't want to apply the SHA-1 to this like silly constant string value. They thought the compiler would do that for them. But if you inject arbitrary height of call graphs, it becomes incredibly hard for the compiler to do this. Okay, and so like we have a bunch of tricks in LLVM's inliner to handle this exact case, because I wrote this code. Ironically, I wrote this code inside of LLVM, and it failed to optimize it. And so I tried to fix that, and I failed. And I tried to fix it harder, and I failed. I tried to fix it again, and it kind of sort of almost works some of the time. But like you're playing with fire here, right? And so I've often advised people when they are writing these variadic calls, right, try and find a way to take it out of the variadic space fairly quickly. Don't build up loads of computation in this like deeply nested call stack with tiny pieces of it at each layer that are hard to analyze, right? At some point, like give yourself an initializer list or an array somewhere on your stack, right, and write a loop over it, and it'll be preposterously faster, okay? It'll optimize so much better. Anyways, so here's like practical lessons you can take away about the inliner. All right, how are folks doing? Folks kind of like dragging a little bit? How much time do we have left? When do we get kicked out of here?
We can have it all night.
Okay, so let's look at memories, loads, and stores. See how much more I get through. Okay, so let's look at some memory things. So if you were paying really close attention, you might have spotted this earlier, but I didn't pay a lot of attention to it. I'll add one more minor construct to LLVM's IR that you need to know about, and this is this allocate instruction. It doesn't do a whole lot. It allocates space on the stack. It's not a big deal. It gives you a pointer to memory back, right? And so here we actually have memory. We have an allocation, we have a store, we have a load. Pretty straightforward. In fact, this is exactly what Clang emits, right, before we do the cleanup and we form this very nice SSA form on the right-hand side, right? So here where we store C and then we branch and we store a different value, right? When we go and run the cleanup passes, we're going to thread all of that memory through so that we have just a phi node between C and D, right? This is what phi nodes let us do. They remove memory from that memory abstraction. Okay, but this is the easy case that we just do when we're cleaning up code. We're not even trying hard when we optimize this stuff. Okay, but there are harder cases that we have to reason about, and they're interesting, harder cases that really come from abstractions programmers introduce, not from anything very fundamental. So this is a little bit bigger. So let's try and step through this. So what happens if I have a structure that I allocate? So here, I am allocating this %s, okay? And what this is we can name types and we can refer to them later. So this %s is a struct with 3 32-bit integers in it. Nothing fancy, 3 32-bit integers, okay? And here we have this get element pointer instruction. And remember I mentioned this is doing essentially pointer arithmetic, all wrapped up in a convenient instruction for you. So we take this pointer to a structure, and we say that we want to go to 0, and that's the index of the pointer. So there's only one s struct here, so it's always 0. And then a 0 index into the struct itself. So this gets us the address of that first integer. Here we get the address of the second integer and the third integer. Right? Nothing too crazy. Then we store into them. So we sent C into the first integer and 0 into the next 2 integers. okay? And then we have some more stores off of these addresses in the then block. Then we load everything back up, we sum some things, and we return a result. Now this is a bit trickier, because here we don't just have like a very trivial stamped out pattern from the front end, right? That's not what's going on here. Here we have this like indexing memory offset stuff going on, and we have to actually somehow realize that these indexes actually all line up, and that these are 3 independent memory locations, and that we can treat them independently. So the first thing LLVM does is it actually partitions this memory. It finds every access to the memory, and it figures out which bytes of memory are actually accessed. And it builds this partitioning across the memory. Once it's partitioned the memory, it tries to say like, well, if I partition memory in this way, can I actually line up the accesses without crossing between any of the partitions? It's like, yeah, actually, we can totally line up these accesses without crossing the partitions. Great. So then it rewrites them in that trivial pattern, which is a step of canonicalization, so to look exactly like what the front end would have put out for an independent variable. And then the cleanup pass fires again, and it rewrites that now single integer 32 loads and stores into a nice SSA register. And it ends up looking something like this. All the memory allocation is gone. All the stores are gone. And instead, we are just selecting between these different scalars. And here we can see that there are 2 partitions of interest here. That's interesting, because we stored to 3 partitions, but there are only 2 that are left, okay? The reason there are only 2 that are left is that we didn't change all of the partitions, right? One of these partitions, this adder 0, stayed the same the entire time. So we don't have to have a fee between that at all. We actually just replace the load of adder 0 with %c very directly. Okay? But for the others, we have this complex mutation across the control flow graph. So we have to build 2 slices where we actually do fee nodes to handle the control flow. On one of them, we take zeros for both, because we stored 2 zeros over here. The other one, we take D and E, right? Because we stored D and we stored E here. Making some sense? Yes? Yes, this is scalar replacement of aggregates. Yes?
So is fee more like a delegate function where based on certain conditions, like a compare whether it should be greater than or less, should be sorting based on greater than or less than?
What is G?
Fee.
Fee. No, it's not. It doesn't look at the values at all. It looks only at the control flow. Right? And it's only like we know whether we pick %d or 0 for this value based on whether control flow comes in through from the %then block or from the entry block. Right? If it comes from entry, we pick 0. If it comes from then, we pick d. Yes?
If you take a pointer to the struct and pass it to another function, does that completely turn off?
Totally turns all this off. There's no way to do this anymore, right? Because I don't know what that other function does. All of this was possible because I could partition every access to that memory. So this access was this very narrow region. This other access was this other narrow region.
Yes, but I was driving at it, it says it's still to the original aggregate, it's just going to pass, take a pointer to the other.
Not really. We use a different technique. We don't do, we don't kind of reform the aggregates on demand. In practice, if any of it escapes, it tends to escape so often that that's actually much worse than the original code. And so we mostly don't do that. We have other techniques that try and handle those cases, but it's harder. Okay, so this is the primary way we collapse these memory abstractions. Right? And there are more advanced things that we will do in some cases, but this tends to be the primary abstraction collapsing thing. Everything else is trying to reason essentially from first principles about what value is stored in memory. Make some sense? This one is the only one that's kind of weird because it doesn't even reason about them from first principles. It's because we can do something better than that when we partition all of the accesses into kind of fields. Okay. So do we really need to look at loops? I can do loops, but I have to be a little bit quick. Otherwise, we're going to run out of time. And that might be OK, because really, how many folks here think that like optimizing loops is super important in C++? Some people, look, if you cared about your loop code, why aren't you writing Fortran? Sorry, it's my best joke in here. I can't miss it. So like maybe, I mean, Fortran is a beautiful language. How many folks here have written Fortran code? It's a gorgeous language. I actually really like it because it's a higher level language. It's beautiful for what it tries to do. But I don't really recommend writing general purpose software in it. It's kind of a pain. It's not entirely fun. But C++ is also really heavily used in contexts where loops matter. If anyone's not familiar with Eigen, it's just a phenomenal example of kind of a practical use of C++ for very loopy code. It's also a phenomenal example of creating the most incredibly hard to collapse abstractions in C++ you have ever seen. I've never seen so many function calls inside of loops that were meant to be fast. It's a thing of beauty, or something. Eigen is a C++ metaprogrammed linear algebra library. And when I say metaprogrammed, it has high-level mathematical optimizations of linear algebra operations by forming expression templates and then kind of reflecting on them in template metaprogramming space and reifying them into beautiful code sometimes or horrific code other times. And it doesn't use any of the fancy things that like Eric Niebler has built to do this sanely. It does it like from scratch. Old school, it's painful. Anyways, let's look briefly at some loop stuff. This is my favorite loop to optimize. So, we have this is simple, this is like, what could be simpler than this loop? Right, like, reference? What, I'm sorry, what? After auto? No, this is simpler. This is way simpler. This is an integer, man. I don't need to like keep it in memory. Like, this is fine. This is the LLVM IR that is produced for that loop. Yeah, so let's go through it. Maybe not. So let's start a little bit simpler. So this is what we get out of the LLVM optimizer. Sorry for changing syntax highlighting on you. Different iterations of this talk. So let's go through this a little bit. You've got, this is what it looks like after the cleanup passes, the basic stuff has been kind of filtered out, okay? And I was actually really impressed when I saw this, because this is actually really simple. I was so impressed that we got to hear from like a really, there was a standard library, there was a std vector in there was a range-based for loop. All of that melted away, right? We actually collapsed all of those abstractions. We got a loop in LLVM IR. So let's look at how this actually works. So first we compute the begin pointer, okay? Which actually kind of does what it says. It's the begin pointer of the vector and the end pointer of the vector. And these aren't actually the begin and end. These are pointers to begin and end inside of the vector object, because it's a struct, right? So what we're doing is we're indexing the struct here to find those elements of the struct. So then we load the begin and the end, right? Cool, now we have begin and end, makes some sense. We branch to our loop head. Loop head, we pick up a pointer, which is kind of the pointer into this vector. Of course, we start with begin if we come from entry. We pick up x, which is our value, our sum, and we clearly start the sum at 0 if we come from entry. We compare to see if the pointer's at the end. Because the pointer's at the end, we've got no more data we can load. And if so, we branch to exit. If the pointer's not in, though, we can actually load some data. And so we load that data out of the pointer. We compute the next pointer, right? This is just adding. Or sorry, this is the sum. And then we compute the next pointer here. Okay? Now it's interesting, right? So our sum, this is how a sum works in a loop. Because we have this, right? We don't ever change the label. We don't actually assign anything. So what we're actually doing is on each iteration, we start off from this x, which is the previous iteration, and we add on to that x here to build x.next, right? A brand new value. But then when we branch back to the loop head, right, and we come from this loop latch, we pick up x.next as the next iteration starting point. Okay? So this is how loops end up fitting into the exact same IR construct. All it is branches and feed nodes. There's nothing else going on here. And of course, like when we're done, we just return x. Make some sense? So loop actually fits on a slide. I was so happy when I did this. And I actually really did compile this code. Like I didn't like craft this example manually. All right, but this isn't how LLVM wants to look at loops. It wants to canonicalize them right, in order to have fewer patterns. Because there are a lot of ways you might choose to structure this. So the next step LLVM does is it applies a series of kind of loop canonicalizations to make the loop look the way it wants the loop to look. So I have all these kind of crammed into one slide here, but the first one, the one that you really need the previous version to see, is one thing that's really annoying about this is we enter the loop in every case here, right? And so kind of whether we actually have a loop at all is determined within the loop with this first comparison. So one thing that really simplifies loop analysis is to actually factor the first comparison out, so that we essentially have a rotated form where the body of the loop is always executed only when you are actually going to iterate, right? So we only enter the loop when we're actually going to do some addition. So that's the first thing that really helps. And you can see how this happens here. So here we have this precondition that we compute, where we test if begin is equal to end, which might be how you would even write a condition in your code, right? And based on the precondition, we either skip the entire loop by going to exit, or we go into this loop PH. And loop PH here stands for the loop pre-header. This is a dedicated basic block whose only purpose is to come before the loop. It's a pre-header. So if you enter the loop, you will go through this pre-header block before you enter the loop, and you will only go through that pre-header block if you're going to execute the loop, right? This is really nice. You'll see why this is so important coming up, okay? So then we had the loop body, and this looks fairly similar. It's just that some of this has kind of been moved around, right? We still get 0 for x to start. We get begin for our pointer, right? But we immediately get to load, right, the next value. We do the sum, we compute the next pointer, and we compare against the end all in one go. And if the comparison succeeds, we continue to loop. And if the comparison does not succeed, we go into loop exit. And loop exit is kind of like a loop pre-header. It exists only to be a loop, a block after the loop. And so the loop exit block is only executed if you did loop, right? And is always executed as you leave the loop. Also turns out to be really important. We do one last piece of canonicalization in here. So we actually use this x.next. That's the sum. So we have to use that after the loop is finished. And we want to really make it easy to find the things we used outside of the loop. So if we use a value outside of a loop, we add a phi node. This has the same semantics as all the other phi nodes you've already seen. But it's a degenerate case. It's not an interesting case. We didn't need a phi node here because there's only one predecessor to this basic block. There's no merge in the control flow graph here. But we put this dummy phi node in, and we actually ensure that it's there because we can have a phi node for every value that lives out of the loop. And because of that, no matter how big the loop body is, if we want to know what values are used outside of it, we go to the exit block and we look at all the phis. And those phis enumerate the things that live out of the loop. What if the loop has multiple exit blocks? Excellent question. Then we have the same pattern for each exit block.
So you have multiple loop.exit.
We'll have an exit block for each loop exit that we need to. Now, if we can, we actually do some work to common them because it simplifies the analysis. But if we common them, we can't do that if it introduces a non-loop predecessor, right? So we actually split off dedicated exits for all of the exiting paths of the loop. But you might have things that you can't merge with this. For example, you might have one loop exit which branches to this exit block. You might have another loop exit that returns. You might have another loop exit that throws an exception. There are many different things, and those we won't be able to merge, and so we'll have a different exit block for each of them.
What about the other case where you have like a jump into?
So what if you have a jump into the middle of the loop from the outside? So we don't call those loops in LLVM. We very cunningly call those irreducible control flow cycles, and we don't optimize them. And we have a bunch of passes that try to regularize control flow and essentially try to remove irreducible control flow. It turns out that is the hardest form of control flow graph to optimize by a huge margin, and it doesn't come up much in practice. In practice, you can almost always peel off iterations to remove the irreducible control flow. Like if you imagine like a Dust device, you peel 3 iterations off of it, and now you don't have irreducible control flow anymore. And that's always the preference for LLVM. All of the algorithms around loop analysis are better in the absence of irreducible control flow, where you have a single basic block which dominates every block in the loop. Yes?
Why do we need a loop
What? Hang on. I have a slide for that. So what if I change end to be a constant? So before I loaded end out of the vector. What if some other optimization pass says, haha, I've discovered what end is. End is 4 elements past begin. Precisely 4. The pre-header one's later, I'm sorry. Hang on to your question. I do have a slide for your question. This is the first fundamental loop optimization, though, especially that collapses the abstraction. So what if I discover the end is 4 past begin? So we don't actually need a loop here, right? But how many folks here have written a loop with like a constant like trip count because they didn't want to write the same code like 8 times? It's really lame, right? Like everybody's done that, right? How many people here have used a macro to do that? You can admit it. Shame. Okay, like you shouldn't use a macro, you should use a loop. But if you're going to use a loop, you better have a compiler that can collapse that abstraction. Because here's an abstraction that is not fundamental to your code, right? It's just for you, the programmer. You want the compiler to remove that kind of thing, right? So this is how this works. So we have this 4. We know how many iterations are going to be. And what the compiler is going to do is it's actually going to use this structure to figure out how to unroll that many iterations of the loop. Because it knows what happens if it has that many iterations. It knows everything that lives out of the loop, right? It knows everything that is definitely executed by that loop. It can just stamp out the code 0, 1, 2, 3 times and take the last one and plug it into the result, right? Very, very straightforward. This is a wonderful transformation, right? And so unrolling like takes a loop and makes it not a loop. Beautiful collapsing of abstraction. Okay, now I will answer the question of why you want a loop pre-header. Questions about unrolling before I jump forward. All right, now let's look at why we need a loop pre-header. So what if we have this load in here of first? Okay? So we have this load every time through the loop, we're loading from begin, okay? And then at the end, we take this first that we loaded. It lives out of the loop, so we've marked it here. And then we use it down here, and we scale something by the first element of the loop. I don't know why you would do this, but some example code, okay? So what the compiler is going to do here is it's going to kind of analyze, can this load ever like change as the loop runs, right? And it's pretty easy to look at the loop and figure this out. We know all of the instructions that participate in this loop, right? It's one basic block as it happens. We can look at them. We have fees, those can't change memory, right? We have loads, those can't change memory. Adds, can't change memory. Indexing, compare, none of these can change memory, right? So memory is the same at the beginning of this loop and at the end of it. And so we can take this load and we can move it out of the loop. Now in this case, this load isn't actually used inside of the loop. So it's even easier. We can actually just sync it into that loop exit block. This is the other reason we need a loop exit block. But if this load were used in the body of the loop, we couldn't make that transformation. But we could hoist it. And we could hoist the load into the pre-header. So the pre-headers and the pre-header and the exits essentially provide a location to move loop invariant code, okay? You always, you never change the semantics if it's invariant, right? You don't execute the pre-header unless you're going to execute the loop, right? You only execute the exit if you did execute the loop. And so it's trivial for us to figure out where to move code. It turns out this is a very important abstraction. Everyone writes loop invariant code inside of their loop bodies. And they rely on the compiler to just lift it out and sync it out, right? And this is how that works. And this very particular pattern makes that incredibly easy compared to if you had to do it from first principles. Make some sense? Answer your question?
But will it be elevated doing the
Yeah. When we go to emit code for it, we of course collapse that away, right? But it turns out this is useful to make loop transformations dramatically simpler. Other questions? But happy with my loops? So I had one more example here that I'm going to skip over because it'll take me forever to explain it. And that's vectorization. But if you want to talk about this, like, we can follow up. I'm happy to talk about vectorization. But like, it's multiple pages, right? It's nuts. Okay. So what happens when these abstractions are combined? Right? Like, we've talked about each of these, how we optimize functions, and how we optimize memory, and how we optimize loops, all of them independently, right? None of them at the same time. And the answer is nothing good. This is actually the killer. Okay, this is the killer for the optimizer. And so let's look at this code. This is kind of my, it's a little bit trivial because I have to make it fit on a slide, but this really is one of the most frustrating parts of optimizing C++ code. All right, so we've got some code. And we are going to use an output parameter here to get C out of G. Now, why would you use an output parameter? Doesn't copy, right? This doesn't copy anything. And that is true. I cannot deny that this doesn't create any copies. But there's something else that it creates. So because we have this little reference here in order to have an output parameter, C actually can't be, like, has to be in memory. Because this reference is a C++ thing. What this actually gets generated into as code is a pointer, right? So it has to have the address of C. But if it has the address, we can't collapse that memory abstraction the way we kind of planned on collapsing it. And if we can't collapse that memory abstraction, we also don't know of any way to, like, reason about these operations, right? Like, this memory is now kept alive. And the reason it's kept alive is because of a function call, okay? That's problematic. Because what if it's the function, like what if you're trying to eliminate this function call? Well, you might want to reason about the math, right, and what the value is. But if reasoning about the math requires you to reason about memory, but the memory is stuck around because you have a function call, but the reason you were trying to reason about the math in the first place is to get rid of the function call, you're gonna have a hard time, right? These things end up being highly interdependent. So please write this. Use return values. Copies are good, right? They're great. I mean, like, they aren't once they're a problem, but I think that the problem of kind of output parameters is much greater than the problem of extraneous copies, okay? So use output parameters. But let's look at a more nefarious way to get to the same problem.
But what if you needed two output parameters?
You could return two things instead of one thing using a tuple. And in C++ 17, your code won't be miserably ugly. Before it'll be mostly ugly. Sorry. Okay, so let's look at a more nefarious example. And this actually comes up all the time in real code. And it's much harder, I think, in my opinion. This one I struggle with how to fix. So here we have a boring struct, right, with some data in it, and a compute method, okay? And this compute method, maybe it's out of line. Maybe it's in some other file, right? You don't know where this compute method is, somewhere far away. So you do a bunch of work here, a bunch of expensive computation, right? This is like lots of things. And then you have this big compute method, right? And you're trying to optimize this, but there's a problem here because S is going to be stuck in memory. Why? I didn't pass it as a reference argument. Well, but you did. Because when you have, like, there are no references here, right? There are no pointers here. It's magic. Because you have a member function, and the member function gets a this pointer argument. And that pointer argument is a very real thing. People like to imagine it's this, like, notional, like, wonderful, beautiful thing that goes away. It's not. It's actually in memory, and it has to be. And it's really hard. If I don't see the body of compute here, the compiler has essentially nothing it can do but assume that you actually use your this pointer as a pointer and do stuff with it, right? And that's miserable, because it means all of this stuff has to actually be written out into memory in the exact representation of S, right? In time to call this compute method, even if that wasn't necessary at all, right? And so you might find out, interesting things about this as you're optimizing your code. And you might want to use this interesting constant, so C here is a constant, right? And you might be like, hey, look, some of the time, I'm going to have a constant in delta, and maybe compute, when delta is a constant, compute, it does nothing at all. It's trivial. It's a trivial function, right? But if C isn't a constant, well, then it's a big, giant pile of goo. It's like our fancy sort, right? And so you really want to know whether delta is a constant when you're making this inlining decision into s.compute. Like, you really want to know that. You'd like to know that. But unfortunately, C is not a constant when you call compute, because C is in memory. And so when you're going and analyzing the body of compute, you actually have to like all you see are loads from memory. You don't see a constant that moves in there. You see stores and loads to memory. So you have one abstraction, stores and loads to memory, another abstraction, function calls. And in order to make the right collapsing decision about function calls, you have to not have the other one. But until you do that inlining, you can't get rid of the other one, right? And this actually comes up. Like, this is a serious thing. Member function calls and output parameters actually pin things into memory that shouldn't be there, and they make the inliner's job harder, and in some cases measurably harder. So my hash example, a lot of libraries are out there which actually do a member function call on the state for their hash object, right? And it's a variadic member function call. It's great, right? You've got a variadic function call, so you create an enormous call stack, and it's a member function each time. And so each time you re-escape all of the state of that memory into memory, like all that object into memory. So if there's a constant propagation, it does not happen. Like, you're just dead in the water, right? Turning that from a member function call to a normal function call, passing it by value, in several cases actually improves performance. Yeah?
What I was alluding to with SROA being defeated.
Yeah, I know.
Just call a member function.
You defeat it as soon as you call a member function. And so please, when you can, and like this is better, because now this, even though we pass an entire struct here, because this is passed by value, compilers are really cool. They're really smart. They see that you're passing a struct by value, and they look at that struct and they're like, I could put that struct into registers. I don't have to give it memory. They'll splat it out across registers, right? LLVM will actually see a constant C in an argument here if we ever prove that this condition is true. And then the inliner gets to see that, and then we get a better inlining decision, and this trickles on down and on down. So, question?
Doesn't that defeat the purpose of classes?
Doesn't this defeat the purpose? Well, I said I was conflicted about this. My problem here is that I like member functions sometimes. Like, I really like member functions sometimes, but they come at a cost. Which brings me to my conclusion. Great plant, by the way. So I don't have an answer. There's not this like recipe, like, here you go, off to the races, your code is now compiled and optimized well. That's not the point of this talk. You may have thought that was the point of this talk, that wasn't the point of this talk. The point of this talk is that there aren't simple answers. You will actually have to reason about what problems the compiler faces and how it approaches them and how it solves them in order to actually make your code really efficient and have really good performance, right? That's actually the point here, is that you'll have to think about this. Sometimes you want a member function. And like, that's the abstraction that makes your code easy to reason about, and it's okay because you've thought about the performance implications, and that's not gonna be a problem for your class, right? Other times it is. And it's going to be a huge problem, and you need to find a way to not use member functions, or to like separate out the code that the inliner has to reason about from the code that uses member function calls, right? You need to actually like partition your code in a way that makes it easier to reason about each layer independently by kind of breaking apart these abstractions. Yeah?
The function is in there, but it's in the header file.
Yeah.
Then the compiler can do the really
Well, we can't inline this thing unless it's in the header file, right? But I'm talking about the case where it is in the header file, right? Right. I can see the body of compute. The thing is, it's got like lots of freaking code in it, and the only way compute simplifies is if I know, if I know that the C happens to end up as the argument. But this is stored to memory, and I can't get rid of this store to memory until this is inlined, right? And so there's this catch-22. This doesn't come up that often, right? I don't want to scare everybody. I don't want everybody to go like, oh my goodness, my code is slow everywhere because of this. I want you to understand how it can come up, because when it does, it will surprise the hell out of you, right? It's not what you expect.
You know that our
value references, our pointers are in memory. You get nothing. Yeah. No. No. Const is meaningless. Sorry. It's not entirely true. There's like two cases where const is like really important meaning. It's never the case you wanted, and it never helps. Like, just never helps, right? Like const has meaning when you put const on a local variable. But like it's a local variable, the compiler probably got it. Like the compiler probably didn't need your help. It technically has some interesting meanings on globals, and I don't know of a single compiler in the world that is effective at using them. And that's not because it's hard, it's because it doesn't help. Right? Like, so what? Oh, sure, but like the places where it would be helpful would be in these like parameters here, right? But constant a parameter doesn't mean anything because I can const cast it away. Const has meaning when you create a const object, not when you create a const reference or pointer. It's unfortunate, but reality. We're clearly well into question and answer.
So the LLVM environment is run the compiler, generate the code, and then do a link. And so stuff that's been optimized in one thing cannot be combined with another. You have to make assumptions. My understanding is the Microsoft compiler actually can do some of its optimization and whatnot during the link phase to solve some of these issues.
LLVM can too. GCC can too. I'm not trying to like pump up LLVM here. GCC has link time optimization. LLVM has link time optimization. Microsoft calls it link time code generation. ICC has whole program optimization, but I don't think it actually works. That's not a knock on ICC. So there are problems with it. It doesn't scale very well. So as you make programs larger and larger, the efficiency of the optimizer itself gets lower and lower. And so to a certain extent, yes, you can solve some of these things by waiting until link time, but you
So at this point that we were just talking about, it could be resolved.
No. So this, sorry.
Yeah.
I changed mid-example, my bad. This, you have the definition. Maybe because you do link time code generation, maybe because it's in a header file. That doesn't matter. Even though you have this definition, you can't do anything with it until you analyze the call site to connect a constant, right, to a particular call site where the optimizer like deletes this else block for some reason and says, it's always a constant, right?
But don't you then have that definition?
Oh, sure. I know this is always a constant here, but then I store that constant into memory. And what I pass here is a pointer into memory. I don't pass a constant in. And so now I have to prove something that's hard to prove. I have to prove that in the definition of compute, where maybe really far down in the function, it loads out of memory this fourth value, that loaded value is in fact the same one that's stored here. No other store clobbered it, nothing aliased it. You have to do all these like magic, and I'm telling you, there's no compiler in the world that does it. Like, doesn't happen. It's too complicated. When we're making the inlining decision, we consider inlining every single call site in your program. Okay, that's a lot of call sites. That's order of edges, not order of nodes. So it's quadratic for a fully connected graph. Fortunately, most programs are sparsely connected, but we still have to be careful there. And so the amount of time we can spend deciding whether to inline this is very tightly constrained. Proving aliasing properties of stores in one function to loads in another function is really hard. And so no compiler can do that.
Style of data flow analysis, vectors or node chains?
Almost all of the data flow in LLVM is based purely on SSA form. We don't do a separate data flow analysis because we started off with SSA form. Like Microsoft's compiler, GCC, both have non-SSA form data flow analyses because they had non-SSA forms right? But LLVM never had a non-SSA form, and so SSA form gave us so much data flow, we never felt compelled to build another one. And we spent all of our time getting things into SSA form rather than doing particularly interesting data flow analysis. The closest we do is we do some analyses over memory, because clearly memory can't be an SSA form. And so we will try to build a memory SSA form to do data flow analysis on memory values where possible. And if you look up the papers about memory SSA, you can see how that works to build you essentially a data flow equation for memory. Everything's based on SSA form. We do have some range analysis, some value range analyses that are on top of SSA form. And right now, all of LLVMs are demand-driven reverse analyses. They essentially start from some use of a value, and they walk up to try and figure out if there's a range constraint on that value. And they're really slow and kind of a pain to use as a consequence. But no one's written what GCC and ICC and Microsoft have. I don't know if Microsoft does. GCC and ICC use a more traditional forward propagation VRP, value range propagation pass, that kind of propagates range information into the program and then can analyze it very quickly. I don't know if that really answered your question about data flow, though. Okay, good.
Does LLVM do any function versioning? For instance, taking the test compute, having a version that knows it with pass C?
The question is, does LLVM do any function versioning or specialization of functions? And the answer is not really. GCC does a lot of that. LLVM kind of oddly doesn't.
That example of this case for doing it potentially, and instead of having the common version of it, you call push it up into the if, so you've got a specialized version and non-specialized version.
So I kind of hear you, except. So the interesting kind of except here is the thing you have to do to know to specialize a function or version a function is the exact same analysis you would do to choose to inline it. You have to have some reasoning about the body of the function that says, there's a predicate that simplifies this thing. And so we could use that same logic to both specialize and to inline, but that logic would be thwarted by the same aspect of this. That logic would have to reason about memory in a complex way. And so whether you're trying to specialize or inline, this will still be a problem. And then there's kind of this awkward realization. So some of the same people who added function specialization at GCC work on LLVM. We haven't added it. The best explanation I have is that LLVM's inliner and GCC's inliner actually, the thing that is most LLVM specific here is actually the inlining discussion, because no one knows how to build a good inliner. Everyone's trying their best, but they're all terrible, right? And so LLVM's inliner and GCC's inliner are remarkably different. And one way that you could kind of compensate for weaknesses in your inliner is by doing function versioning or specialization. LLVM has not needed to do that because of how its inliner tends to work. Function versioning and specialization tend to help when functions have not been simplified yet, but you know there is interesting context. And so you don't know if it's going to matter enough to inline, so you version them so that you can make that decision later, right?
I guess that kind of goes back in a lot of ways to the trying to do an optimization. And if you could, then maybe you would more often.
Right, and so because GCC and other inliners tend to proceed top down instead of bottom up, they tend to see a lot of kind of unoptimized code in callers. And so they'll specialize that in some cases based on context, so that then when they go to optimize it, they can leverage that, right? But they don't know enough to inline. What we see with the bottom-up inliner is that you don't have to do that. You end up actually, for all the interesting call sites where you might want to specialize, you end up having small enough amounts of code left at the end of it that you can actually inline it. You don't need to create a version of the function for it. And so the important places where that optimization fires in LLVM, we've gotten lucky in the inline. And I'm not trying to say that makes LLVM's inliner like better necessarily. There are plenty of alternative scenarios where the approach LLVM takes looks really bad, and the top-down approach GCC takes looks way better, right? So it's a trade-off. It's always a trade-off here. But one kind of consequence of the trade-off is that we have a relatively low requirement for specialization or versioning. The only current really big motivation to do that in LLVM that I know of from talking to people is around things like vectorization or specialized hardware versions, which is a totally different use case for version. I don't know of anyone who's really hit a lot of issues where versioning or specialization would help kind of basic abstractions like this. Also could be just I just don't know of them. Always a possibility. ABIs, that's the other place where versioning kicks in, is sometimes ABIs make it hard to not version things.
About partial inlining? Like, can you like break a function into like multiple functions? One of them is really simple, it can be inlined frequently, and one of them is more complicated.
This is something that there's active work going on in LLVM on. Actually, this is the optimization that got me started working on LLVM's inliner 5 years ago. And what I wanted to do is partial inlining. And I had this idea that the right way to approach partial inlining was actually to not do partial inlining at all, but to do outlining. Essentially, when we see like this nice call graph, some of the time, rather than trying to inline pieces of it, we'll actually say, like, look, there's a pile of complex code here that seems essentially separable from the rest of your code. And I have some reason to think I should try and separate it. So I'm going to sink all of that into some helper function and prevent it from getting inlined back, right? And now I have a simple function body, and maybe that gets inlined much more easily. And that's one way to approach partial inlining. You can approach the problem as an outlining problem that kind of interacts with the inliner. This has some advantages in that you also get code size savings in a bunch of cases that you might like. It is also particularly amenable if you use things like linker order files to kind of like lay out your binary so that the hot functions are kind of all together. Then outlining is way more interesting in some ways than partial inlining. But it also has some downsides in that it's not partial inlining. And so there are places where outlining fails even though there's a great partial inline candidate. And so someone else is actually currently looking at whether we should instead go with kind of more traditional partial inlining. I don't really know the answer. My suspicion is, from what I've seen, the partial inlining case is actually, the interesting cases that outlining doesn't cover aren't useful. They're too hard to get ever, or you get wrong more often than you get them right. And so I'm personally more interested in the outlining cases because those are actually the easy cases, right? Where you have kind of a clear, like a hot path early exit from your function, and you're like, that cold path that has all the code in it, like all the logging code for my error handling, I don't want that in the same function body. I'm gonna split that off, right? I'm personally a fan of this. Does this mean that functions which get pointers or references as arguments?
Because this can forget that these is a pointer.
Yeah.
There's no memory for the key.
Yeah.
For example, just like regular function that has the pointer as the parameter. Okay, I don't get it.
Right. I mean, yes and no. It's not harder to inline, right? It's easy to inline. It's harder to analyze because there's memory, right? It's harder to analyze because we combine two abstractions. Now, maybe that doesn't matter. Like, this is clearly a simple function. We're not gonna have any trouble telling that, right? Like, this memory is not gonna confuse us in this particular case. But the analysis problem is now a harder problem to solve, right? At some point, you'll fail. I really hate std swap, actually. There's a good thing about std swap, though, and that's that std swap happens to contain no code. It just calls something else, or it's like trivial, and so we're fine, but almost out of luck, right? Like a lot of STL things, which kind of like they deduce template arguments, right? And they'll very often like always deduce a reference argument because that's how STL deduction works, right? Like, oh, it's tref, right? Like, I don't know what kind of thing you give me, but I'll take it in, right? Those are kind of miserable because they always put things in pointers. Fortunately, they also tend to be very small, and so we tend to get rid of them and then stitch things back together, but yeah, it's a real pain. The STL is actually kind of hard to optimize because of references and deduction and how that ends up working. Oh, he needs us to flagging us down.
It's getting late. Like I said, we do plan to have Chandler back. Well, he will be at CPP.
I will be at CPPCon.
No matter what, he is willing to donate more of his time plus we could keep up the discussion. But one more question, and let's move on.
For the record, I'm happy to like sit around outside and keep answering questions if it's cool.
This one does the opposite, right?
Yes.
It knows seasonal parameter, so it converts it to return value.
No. So the reason we can't automatically convert things to return values, this is a good question. So the problem here is that changes the signature of the function. And so that's kind of hard to do. And if we can change the signature of the function, I'll let you know a secret. We'll actually do a whole bunch of other things that make all of these questions somewhat moot. But like, if this is like a function in a header, this is an external function. If there might be some other caller, we can't just blindly change the API of the function. And so that's one of the hardest things for us, is that we kind of are pinned in to the references you put in your type signature, in your signature of your function. But the things that would let us make the copy, or know that making a copy was profitable, are the same things that would let us inline that copy. And so if we knew enough, we would just inline it, right? But we don't know enough, because that copy might be huge. There might be 1 million copies that we make that way. None of them different, right? We don't want to do that. That bloats all of your binaries. It's awful. And so that's the thing. The same analysis we would need to do to make a copy is the analysis we would do to inline, because that's all inlining is. It's just making a copy. It's just inlining a copy. Anyways, got to cut it off. Very sorry.